Hello everyone. In this video, we are going to talk about software style and architecture. Let's talk about why software architecture really matters when you are building a product. When we aim to create a system that's not just functional, but also reliable, secure, and efficient, we need to be intentional about its architectural design. First, we consider the overall organization of the system. How is everything structured? What are the major building blocks? Then we will break it down further, like how do we decompose the system into components. This helps with clarity, reusability, and maintainability. Another big part is server organization, or how the software components are actually deployed across the hardware. This is where we think about scalability and fault tolerance. And of course, the technology choices. What languages, frameworks, and tools are we using? All of these decisions shape the product's final quality. Good architectural design sets the stage for better performance, usability, security, reliability, and how easy it is to maintain and evolve the software over time. So architecture isn't just a diagram, it's a strategic foundation. Let's now dive into what we mean by a component in software architecture. Think of a component as a building block. It represents a piece of functionality, something cohesive and meaningful that the system needs to do. Often, a component will provide one or more services, and these services can be used or called by other components. So, the idea is to break the system into modular, reusable parts that work together. Now, here is something important. When you are in the architectural design phase, you don't need to figure out how the component is implemented just yet. Your job at that point is to define the interface. Basically, what that component is expected to do and how other parts of the system will interact with it. The actual coding or implementation of that component comes later. This separation of concerns helps keep your architecture flexible and scalable as the project grows. This diagram shows two different ways we can structure how services within a software component are accessed. On the left, we have component 1. In this setup, the internal service S1, S2, and S3 are directly accessed by other components. That means there is no filtering or abstraction layer in between. While this might seem simpler at first, it introduces tight coupling, making the system harder to maintain and evolve because other components are directly depending on internal details. On the right, we see component 2, which takes a better engineering approach. Here, services like S4, S5, and S6 are only available through a dedicated API. This API defines what the outside world can interact with without revealing the internal structure. Why is this better? Because the API acts as a protective interface. Other components don't need to know how the services are implemented, just how to interact with them. This creates looser coupling and makes future updates or changes inside the component much easier to manage. So as we move into modern architectural practices, API-based access is generally preferred for its flexibility, security, and maintainability. Now that we have mentioned how architecture affects non-functional properties, let's break down what those actually are and why they matter. First, we have responsiveness. This one's about speed. Is the system fast enough? When users interact with it, do they get responses quickly and smoothly? And next is reliability. This refers to how consistently the system behaves the way it's supposed to. We want both developers and users to be able to trust that features work as expected. Availability is all about uptime. Can the system deliver services when users need them? This becomes really important in systems that have to be online 24/7. Then there is security, and this one's huge. It's not just about locking things down, it's about making sure the system protects both itself and its users from unauthorized access and potential attacks. Usability is a user-focused quality. Are users able to access the features they need, and do they find the system easy to use without making errors or getting frustrated? Maintainability refers to how easy it is to make changes. Can we add new features or fix issues without breaking the system or spending too much time and money? And finally, resilience. This is about how well the system bounces back. Even if there is a partial failure or an external disruption, the system should be able to continue operating in some meaningful way. Each of these qualities should be considered from the start because architectural choices can either support or seriously undermine them. When we are designing software architecture, it's not just about organizing code or picking technologies. There are broader influences we need to keep in mind. First, we have got non-functional product characteristics, things like responsiveness, security, and availability. These aren't about what the system does, but how well it does it, and they are shaped directly by architectural decisions. Then there is the product lifetime. Is this a quick prototype or something expected to run and evolve for 10 plus years? If it's long term, you need to invest in flexibility and maintainability right from the start. Another big one is software reuse. A good architecture can make it easier to repurpose modules or services in other products, saving time and cost across multiple projects. We also consider the number of users. Is the system serving a few admins or millions of users globally? That affects decisions on scalability, load balancing, and infrastructure. And finally, there is software compatibility. If your system needs to integrate with existing tools or legacy platforms, your architecture needs to account for that early on the avoid major refactoring down the road. So as you can see, architecture isn't designed in a vacuum. These five factors help shape smarter, future-proof decisions. Now let's talk about how real-world considerations shape architectural design. We will start with non-functional characteristics, life performance and security. These impact everyone using your system. If you don't get them right, your product might never succeed commercially. The tricky part is that sometimes these qualities um, can conflict. For example, improving security might hurt performance. So you will need to prioritize based on your product's context. Next is product lifetime. If you're building something meant to last, say 5 or 10 years, you can expect it to evolve. That means your architecture should be flexible and extendable so you can add new features without starting from scratch every time. Software reuse is another key influence. Using existing components, whether upon whether open source libraries or in-house modules can save time. But keep in mind, these components might come with their own requirements or limitations, so you may have to design your architecture around them. Now think about user numbers. With online applications, usage can grow or shrink overnight. If your architecture doesn't scale up or down gracefully, you risk performance issues or wasted resources. And finally, compatibility. If your system has to work with other software, maybe an existing database or a third-party platform, those requirements will influence the tools and structure you choose. For example, you might have to use a certain database just because everything else in your client's environment depends on it. So ultimately, designing software architecture isn't just about picking what you think is best. It's about making smart, context-aware decisions that align with all of these influences. Let's finish by talking about maintainability and the trades-off it often brings. Maintainability is all about how hard and how expensive it is to make changes to your system once it's out in the world. Whether you're fixing bugs, adding features, or updating the tech stack, some systems make that easy, others make it a nightmare. So, how do we improve maintainability? The best approach is to build your system from small, self contained pieces. Think of each part as doing one job and doing it well. That way, if something needs to be changed or updated later, you don't have to touch the whole system, just that one part. We call this fine-grained decomposition, breaking the system into components that each serve a very focused purpose. But there is a catch. More components means more communication between them. And that communication isn't free, it takes time. So, if a single product feature requires a bunch of components to work together, that overhead can slow the system down. That's the trade-off we often face in architecture, balancing flexibility and maintainability with performance. And as designers, it's our job to make those calls wisely based on the needs of the project. Let's bring together what we have learned about database architectures with a side-by-side comparison of two designs. In the first diagram, we see a shared database architecture. Both C1 and C2 depend on the same central database. This setup is simple and efficient in terms of consistency. There is only one source of truth. But here is the downside. If we want to make performance improvements for C1, say by restructuring its data access or schema, those changes could negatively affect C2. You are essentially trying their behavior together, even if they serve very different rules. Now, in the second diagram, we explore a more modular architecture. Here, C1 and C2 each have their own database, tailored to their needs. That means we can optimize C1's database structure without worrying about C2. So, sounds great, right? Well, not so fast. This architecture adds complexity. Now we need a third component C3 whose job is to keep the database in sync. This is called database reconciliation. While this separation improves flexibility and reduces interdependence, it introduces new costs, both in terms of development and ensuring data consistency across the system. So, as always with architecture, it's about trade offs. If your system needs high performance and loose coupling, separate database might be worth it. But if consistency and simplicity are key, a shared database might be a better choice. Let's talk about one of the most important and sometimes frustrating parts of system design: security. One highly effective approach is to use layered security. You can think of it like an onion with multiple protective shells that an attacker would have to get through to reach the core. At the outer layer, we might have IP authentication, which filters access by network. Then we move to application authentication, where users log into system. Beyond that, we could have feature level authentication. So even if someone's logged in, they don't necessarily get access to everything. Encryption adds another critical layer, making sure that even if data is intercepted, it's not readable. And finally, at the very center, you've got your protected assets, like a database of users' credit card information. Now, here is the trade off. While layer security is great for protecting systems, it can negatively affect usability. Users might have to remember multiple passwords, go through re authentication steps, or deal with access delays. And many find this annoying. In fact, it's not uncommon for users to look for shortcuts like writing down passwords or typing to keep sessions open forever, which ironically weakens the very security we worked hard to put in place. So, as software architecture, our job is to balance security and usability. Strong protection matters, but not at the cost of user frustration or risky workarounds. As we wrap up this discussion on security and architecture, let's talk about how to avoid turning your system into a usability nightmare. The reality is users don't like jumping through hoops, especially when those hoops feel redundant or unnecessary. And while we want strong protection, we don't want to frustrate users to the point that they start finding ways around the system. So how do we balance that? First, don't go overboard with too many security layers. Each layer should serve a real purpose. If you find yourself adding authentication just for sake of it, stop and ask, does this actually help? Second, avoid unnecessary enforcement. If a user is already authenticated at a secure level, they shouldn't have to re-enter credentials or to perform every small task. And finally, provide helper components. These are things like single sign-on, token-based sessions, or integrated password managers. They lighten the user's mental load and keep the system secure without constant interruptions. The best architecture support users, not just protect them. Data. When security is well designed, users don't even notice it, and that's exactly what we want. Let's talk about availability, which is one of the most critical non-functional requirements in enterprise systems. Availability basically means how often your system is up and running, delivering services, responding to requests, and doing what it's supposed to do. It's usually measured as a percentage of uptime. For example, a system with 99.9% availability is down for less than 9 hours a year. Now, this might be a nice to have in some customer apps, but in industries like finance or healthcare, availability is a must have. You simply can't afford downtime in systems handling banking transactions, stock trading, or medical equipment. So, how do we achieve high availability from an architectural perspective? The answer is redundancy. You build backup components into the system, components that are ready to jump in if the primary ones fail. To make that work, you need to a failure detection mechanism. something that notices when a component goes down, and a switching mechanism that redirect traffic or task to backup. But here is the trade-off. Adding these extra layers increases cost, development time, and complexity. And more complexity can introduce more places for bugs or vulnerabilities to hide. So, once again, architectural decisions are all about balance. In high stake systems, the benefits of availability almost always justify the investment in redundancy, but it has to be designed carefully and tested truly. Okay. So, as we step back and think holistically about software architecture, there are a few fundamental questions we need to ask. These questions help guide not just what we build, but how we build it and how it will perform in the real world. First, how should the system be broken down into components? Each component should take on a focused responsibility, contributing a well-defined part of the system's functionality. At the same time, your structure should support your goals for security, reliability, and performance. Second, how will these components be distributed and how will they talk to each other? Are they all running on the same server, separate across a microservices architecture? Should they communicate through direct function calls, APIs, or maybe messaging queues? These choices affect scalability, latency, and failure handling. And third, what technologies and reusable parts will you build with? This includes choosing your tech stack, languages, frameworks, databases, but also thinking smart about what you don't need to build from scratch. Can you use open source components, cloud services, internal libraries? Answering these three questions sets the foundations for a strong, scalable, and maintainable architecture. And they are questions you will return to again and again, not just at the beginning of the project, but throughout its life cycle. As we wrap up, let's touch on one of the biggest challenges in system design, managing complexity. A system gets more complex not just because it has a lot of components, but because of the way those components are connected. All the communication passes, data sharing, and dependencies between them. One smart design principle is to localize relationships. If two components, let's say A and B, interact frequently, it's best to keep them close together, ideally in the same module or package. This makes the architecture easier to understand and reduce the cognitive load for future developers. Next, watch out for shared dependencies. When multiple components like C1 and C2 rely on the same shared database or service, that creates tight coupling. Any changes to that shared element means you now have to analyze and potentially update both components. It slows you down and increases the risk of unintended side effects. A good rule of thumb is perform local data whenever possible. Give each component its own copy or abstraction of what it needs rather than forcing them to depend on a shared resource. This helps reduce ripple effects and improve modularity. In short, smart decomposition isn't just about slicing up functionality, it's about strategically managing relationships. So the system stays understandable, testable, and maintainable over time. Let's take a closer look at the kinds of relationships that can exist between components in a system. Because How components interact has a huge impact on maintainability and complexity. First, we have C1 is part of C2. In this case, C1 is literally embedded inside C2. It's a subcomponent. That means C1 doesn't operate independently. It's tightly bound to the structure and behavior of C2. Next is C1 uses C2, probably the most common type. Here, C1 is calling or invoking a service that C2 provides. There is a dependency, but the components are still somewhat modular. Then there is C1 is located with C2, which is all about deployment. These components might not be functionally related, but they are placed on the same server, virtual machine, or container. This might be for performance reasons, cost savings, or deployment simplicity. And finally, we have C1 shared data with C2. This kind of relationship can be risky if both components depend on the same data, maybe a shared database table or a config file. That creates tight coupling. If the data changes, both components may need to adjust. So while something unavoidable, it's often better to design for data ownership and local copies when you can. Recognizing these different types of relationships helps you design better boundaries between components, and that makes your architecture more robust and maintainable in the long run. Let's finish with a triangle of three essential design principles that can guide you throughout your architecture decisions. First up, separation of concerns. This one's foundational. Um, each component should handle one specific responsibility. For example, if you are building an e-commerce app, don't mix user authentication logic with product catalog management in the same module. Clear boundaries make things easier to understand, test, and change later on. Now we have a scalable interface. Think of this like a contract. You want the public interface of your components to be well defined and resistant to frequent changes. If you're consistently modifying interfaces, you create a ripple effect of breakages throughout your system. Stability here allows you to evolve internal logic without breaking downstream customers. And finally, implement once. Don't copy and paste the same logic across 5 different services. It might seem faster at first, but it creates a maintenance nightmare. Instead, extract shared behavior into reusable components or utility modules so that you only have one place to update if something changes. These three guidance, separation of concerns, a stable interface, and single implementation will help you build systems that are clean, modular, and built to last. Let's define what we mean by subsystem decomposition. Think of it as the high level blueprint of a system, where we break down the system into major parts like subsystems and services and define how they relate to each other. Now, when we follow a recurring pattern to do this, like organizing by layers or services, we call that an architectural system style. These styles help us follow best practices and make our systems easier to understand and maintain. So, in a way, an architectural style is like a design pattern, but for structuring large parts of the system. So as you can see here, we have 5 popular architectural style. So let's check one by one. In a layered architecture, we divide the system into ordered layers where each layer provides services to the one above and uses services from the one below. For example, in a typical web application, you might have a presentation layer, a business layer, logic layer, and a data access layer. Notice that each layer has a one-way dependency. It knows about the layer beneath it, but nothing about those above. This reduces coupling and increases maintainability. We can also partition layers horizontally into smaller independent subsystems. For instance, different modules handling user accounts, billing, or notification might all exist within the same layer but operate independently. These are what we call partitions or weakly coupled subsystems. Let's take a closer look at how relationships between subsystems are structured in a layered architecture. We generally see two major types of relationship. First, there is a use relationship. This means that subsystem A depends on subsystem B being correctly defined and available at compile time. If B isn't there or isn't the right version, A simply won't compile. Think of this as a development time dependency. Then we have the calls relationship. This is more about what happens at runtime. Here, A invokes B during execution. So A triggers some behavior in B. And this forms a dynamic connection between the two subsystems. Now, aside from those vertical relationships, we also have what we call partition relationships. These are more horizontal. In this case, subsystems on the same layer know about each other and call each other services. So it's bidirectional. A can call B and B can call A. The best way to see all of these is action. This is in action is to look at the TCP IP model. This layer to stack is a classic example in network design. On the sender side, we go from the application layer down through transport, internet, data link, and then the physical layer where data gets transmitted. On the receiver side, it's this reverse data moves up layer by layer until it reaches the application again. Each layer adds or removes information as needed, and all layers play a clearly defined role. This layered setup not only improves modularity and separation of concerns, but it also makes debugging and extension much easier. Now let's break down this diagram to really understand how subsystems interact both across layers and within the same layer. First, look at subsystem A in layer 1. It's connected to subsystem D in layer 2 with solid red arrow. This illustrates a use in relationship. What that means is A requires D to be present and correctly implemented at compile time. Otherwise, it won't even run. So this is a classic compile time dependency. Now from subsystem D to subsystem G in layer 3, we see a dashed red arrow. This represents a calls relationship. In other words, at runtime, D is triggering G to perform some behavior. So it is a runtime dependency, only active when the system is running. Then over the left side, you can notice subsystem B and C. They have arrows pointing both ways. This is a partition relationship and it's happening within the same layer. These subsystems are weakly coupled but still aware of each other's services, meaning they can interact without needing hierarchical control. This diagram really captures the essence of architectural layering. It separates concerns both vertically across abstraction levels and horizontally within the same abstraction level. It's a foundational concept in designing a scalable, maintainable system. All right, let's take a look at this diagram and talk about why this subsystem decomposition is problematic. At first glance, you can see that almost every subsystem seems to be connected to almost every other one. And that's a red flag. What this means is that we have very high coupling in the system. For instance, user interface isn't just interacting with the tournament subsystem, but also with component management, session management, and so on. That's a lot of dependencies. Now, high coupling might not seem like a big deal at first, but here is the problem. When everything depends on everything else, small changes ripple through the system. You fix one thing and suddenly three other modules break. That makes the code base really hard to maintain and even harder to scale. Also, there is no clear separation of responsibilities. Subsystems aren't isolated in layers or partitions, which means we don't benefit from the usual modularity that makes large systems easier to work with. So that takes away here is this is exactly the kind of architecture we want to avoid. We will look at better alternatives next, where responsibilities are clearly divided and dependencies are minimized. All right, now let's break down what this slide is showing us. This is a very common pattern you will see in many software systems, what we call a layered architecture. You have got your horizontal layers here on the left, the user interface at the top, and then below the application logic, infrastructure services, the operating system, then finally hardware. Now notice these vertical arrows going straight down. Each of these arrows represent a vertical subsystem, basically a feature or component that spans across all layers. So if you think about something like a login module, it might include UI elements, application logic, calls to infrastructure, interactions with the OS, and maybe even some device level checks. At first glance, this might seem like a clean and logical way to structure a system, and in many cases, it's necessary. But here is the catch. These vertical slices often introduce tight coupling because each feature depends on multiple layers. Any change in one layer can have triple effects across the entire subsystem. So while this layout reflects how software executes, it doesn't necessarily reflect a clean modular design. That's why in practice, we often look for ways to decouple these layers using techniques like abstraction, surface interfaces, or even adopting layers communication protocols to improve maintainability and testability. Now let's talk about one of the most important principles in secure system design, which is the defense in depth. So what you have seen here is a common issues in layered architectures. Vulnerabilities can exist at any level. The browser, the database, the application code, the OS, and so on. And attackers know this. They don't just come in through the front door, they look for any weak spot in any layer. Now, if we really rely on just one component to handle all our security, say a single firewall rule or one piece of authentication logic, that's a single point of failure. If that one thing breaks or gets bypassed, our entire system is at risk. Instead, the smarter approach is to distribute security across multiple layers. For example, input validation in the UI, permission checks in the application layer, secure queries at the database level, and system level policies in the OS. This way, even if one defense is breached, others are still in place to catch the attack. This is what we mean by layered security or defense in depth. It's not just best practice, it's necessary for resilient software design. Let's take a look at what are the layers in a typical web application. At the top, we have the user interface layer. This is where the user interacts with our system entire through a web browser, either through the web browser or using HTML and JavaScript or a native mobile application. Just below that is the authentication and UI management layer. This is where we handle login logic, session management, and generation of dynamic content like personalized web pages. It acts as a gatekeeper to ensure users are who they say they are. Then we have the application logic layer. This is really the brain of the system. This layer carries out the core functions that our application is supposed to provide. For larger applications, this layer might even be split further into smaller components to improve modularity. Next is the shared services layer. These are the utility components that don't directly belong to the application logic but are essential. For example, logging services, notification systems, or shared configurations. Finally, at the bottom, we have the data management layer. This handles everything related to storage, managing the database, ensuring data consistency with transactions, and providing recovery in case of failure. If your application doesn't use a database, this layer might be unnecessary. But in most real-world systems, it's a key component. Now let's talk about why we often use a layered architecture in software systems. First, layers are highly cohesive. That means each layer focuses on a well-defined responsibility, which helps with information hiding. We don't need to know how things works inside the layer, just how to interact with it. Second, we usually design layers to have low coupling, meaning they don't heavily depend on the layers above them. This makes the whole system easier to manage because changes in one layer are less likely to break things in others. Next, layering is a great way to decompose complex systems. Instead of dealing with one big, messy structure, we break it down into manageable parts. Each layer handles a distinct concept. It also helps with maintenance and evolution. Say you want to improve performance or add features, you can often just replace or update one layer without affecting the rest of the system. That's a huge advantage of long-term development. And finally, reusability. Layers like authentication, logging, or database management can often be reused across multiple systems, saving both time and effort. So overall, layered architecture promotes better design, easier maintenance, and more robust systems. While layering architecture offers many advantages, it's important to understand their trade-offs. First, performance can take a hit. When every request or operation has to pass through several layers, even when some don't add much value, it can slow things down. This added overhead becomes noticeable in performance sensitive systems. Second, debugging becomes more complicated. When something goes wrong, figuring out where it broke can be hard. The error might start in one layer, bubbled up through others, or get masked along the way. Tracing that path can take time. Finally, designing the layers correctly isn't easy. It takes careful thought to decide what each layer should do and how it should interact with others. If you get it wrong, the benefits of modularity and maintainability can quickly disappear. So while the layered approach is powerful, it's not a silver bullet. It requires thoughtful design and careful implementation. Next architecture style is model view control, or MVC. Let's see that. When we talk about the MVC, or model view controller architecture, we are referring to a design pattern that breaks an application down into three separate components, each with a distinct responsibility. We start with model. This is the core of the application. It holds the data and the business logic. If you are building, say, a budgeting app, then model would represent things like accounts, transactions, and rules around spending. Then we have the view. This is what the user actually sees and interacts with. It could be a web page, a mobile screen, or even command line display. Its job is to present the data in a meaningful way, but it doesn't hold any logic. And finally, the controller. Think of the controller as the middleman. It listens to the user's input, figures out what action needs to happen, updates the model, and many refresh and maybe refresh the view. By separating concerns like this, MVC helps us keep the code organized, more maintainable, and easier to test. It's especially useful in applications where user interaction plays a major role. So here let's walk through how a typical request follow through the MVC architecture. And I found this image from the link of YouTube that you can find here in the bottom of the page. Everything starts when a user interacts with the interface. For example, clicking a button or submitting a form. That interaction triggers a request, which is first handled by the controller. Now the controller's job is not to handle business logic or data. It's more like a traffic direction. It knows who to talk and when. So the controller goes to the model and to get the necessary data. The model is in charge of all the core logic and data manipulation. It might fetch information from the database or process something internally. Once the model gives the controller the data, the controller passes it along to the view. The view is responsible for rendering the presentation, the part that the user sees. It dynamically updates the interface based on the data it receives. Finally, once the view is ready, the response goes back to the user in the browser. So each component stays focused on its own job, which is why MVC is such a powerful pattern for keeping web applications organized and scalable. So one of the core strengths of the MVC architecture is the clean separation between different parts of the application. The model is entirely focused on the data. It could be talking to a database or handling business rules. The view, on the other hand, is only concerned with how the data is presented to the user, and the controller is the glue that connects them. It interprets the user actions and tells the model or the view what to do. Now, why does it matter? Well, it makes your code much more modular and maintainable. You can out the view, maybe switch from a web-based UI to a mobile one without changing anything in the model. The controller might change too, depending on how users interact with the system. But again, the core data logic stays untouched. And here is another huge benefit because everything is loosely coupled. You can even update the interface in real time. So, for example, you could dynamically refresh the UI with new data while the application is running without having to restart or rebuild anything. That's incredibly powerful in today's interactive real-time applications. Now, the third popular application is pipe and filter. Let's look at that. Okay, so the pipe and filter architecture is a classic and really elegant pattern used in software design. At the heart of it are two simple concepts, filters and pipes. A filter is a processing unit. It takes some input, does something to it, and sends out the result. You can think of it like a transformation step. Maybe it's compressing data, parsing it, formatting it, anything that modifies or processes that the input in some way. Now, how do these filters talk to each other? That's where pipes come in. A pipe is just a conduit. It moves the data stream from one filter to the next. What makes this style powerful is how modular it is. Each filter operates independently and doesn't need to know what came before or what comes next. You can rearrange them, replace one with a new version, or change or chain together different ones to build flexible processing pipelines. This module is especially common in things like compiler design, data processing tools, or even Unix command line programs. It's all about a streamlined data flow through independent processing stage. Let's look at how the pipe and filter style is applied in something you have likely studied before, compiler design. In a typical compiler, we break the work into several phases, lexical analysis, parsing, semantic analysis, and finally code generation. Each of these steps is essentially a filter. It receives some structured input, processes, or transforms it, and passes it along. The connection between these steps, the way data flows from one to the next, is handled through pipes. So you can imagine the source code flowing into the first filter, the lexical analyzer, which breaks it into tokens. These tokens are passed through a pipe to the parser, which builds a syntax tree and so on. This kind of structure is clean, modular, and easy to maintain. If we ever need to replace or modify one phase, say update the semantic analyzer, we can do so without changing how the rest of the compiler works. That's the beauty of pipe and filter in practice. It promotes separation of concerns and makes each step independently testable and replaceable. So compiler design is a great real-world example where this architectural style naturally fits. Now let's talk about why the pipe and filter architecture is such a powerful pattern in software design. One of the biggest strengths is modularity. Each filter performs a specific task, and because of this isolation, we can easily modify or even replace a filter without touching the rest of the system. Another huge benefit is flexibility. You can rearrange filters to change the behavior of your program. So instead of building a new system from scratch, you can just tweak the order of your filters and get a new result. It's a very efficient way to build variations of the same functionality. Also, filters are highly reusable. Once you have written a filter, say for sorting or formatting data, you can use it in multiple projects. Just plug it in whenever it fits. And finally, this architecture is perfect for stream processing, like when you are working with real-time data pipelines or media processing, where data flows continuously and is transformed along the way. So overall, pipe and filter promotes simplicity, reusability, and speed, qualities we really value in software development. And the fourth popular architecture is repository style. So let's look at that. The repository architecture pattern is especially common in systems where data sharing is a central requirement. In this pattern, all subsystems interact with a single centralized data structure, which we call the repository. Think of the repository as a shared database or knowledge base that stores all the data the system needs. Each subsystem doesn't talk directly to the others. Instead, they all access this repository using standardized interfaces like create data, get data, or search data. This means they don't need to know how the other parts of the system work, which makes the system loosely coupled. That loose coupling is a big advantage. Let's go. Sorry. So it improves the modularity, simplifies maintenance, and makes it much easier to evolve parts of the system independently without breaking things. So when you are dealing with applications that rely on a shared body of information like compilers, content management systems, or large-scale data processing pipelines, the repository style is a strong architectural choice. And now let's look at the practical example of how the repository architectural style is used in software development environments. At the center of the architecture, we have a project repository. This is where all the key artifacts of the project are stored: design models, source code, metadata, and analysis results. Various tools interact with this shared repository. For example, a UML editor might update the design diagrams. A design translator could convert those diagrams into a formal specification. A code generator uses the same data to produce Java or Python code. Meanwhile, a design analyzer evaluates whether the architecture adheres to constraints or quality metrics. A report generator pulls everything together into structured data documentation. This architecture allows for tight integration across tools. All components are loosely coupled through the repository, which acts as a single source of truth. That means when one tool updates the repository, other tools immediately benefit from the new information without needing direct integration. The result is improved collaboration, consistency, and productivity in large-scale software engineering projects. Let's talk about the key benefits of using a repository style architecture. First, all subsystems communicate only through the central repository. This means they don't need to know anything about each other directly. As a result, you can easily plug in a new subsystem, update an existing one, or even remove a component without breaking the entire system. This loose coupling brings us to the second point: independence. Each subsystem operates autonomously, and that's great for fault tolerance. If one component fails or behaves unexpectedly, the rest of the system can still function, making the overall architecture more resilient. And finally, because all of the data is stored in one place, the repository, it becomes much easier to manage. You can enforce access controls more effectively, monitor activity, and implement security measures in a centralized way. This is especially useful in large scale systems or environments that require strict compliance and data governance. Now, while the repository architecture comes with several advantages, it's important to also recognize its limitations. The first issue is performance. Since every subsystem depends on the repository for data exchange, the repository can easily become a bottleneck. As the system scales or handles more data, Decentralized communication can slow things down. The second major concern is reliability because the repository is central to the system's operation. If it fails, everything else fails with it. In other words, it becomes a single point of failure. This risk must be managed carefully, especially in mission critical application where downtime is unacceptable. So while the architecture is elegant and clean, these trade-offs need to be considered during design. And the last one is hybrids of style. So let's talk about hybrid architecture because in practice, most real-world systems don't stick to a single architectural style. For example, your system might follow a layered architecture as its overall structure, but within those layers, you could have one that uses in the pipe and filter model for stream processing, and another that follows a repository style for shared data access. Or take the reverse situation. The whole system might be built around the pipe and filter concepts, but inside each filter, you're using a layered approach to keep things modular and maintainable. This kind of flexibility is powerful. It lets you optimize each part of your system based on its specific responsibilities rather than forcing everything into a single architectural module. Okay, so we're done with this chapter and thank you for watching this video.